Next homework is assigned today. Is the same information. Your first lab will be wafer cleaning, oxidation, ellipsometry. So weekly do some oxidation. How do we measure the oxide thickness? How do we how do we define the parameters for oxidation? Temperature, pressure, not necessarily, but what kind? Is it wet oxidation or dry oxidation you want to do? And then do we have native oxide? How do you get rid of native oxide? Once you get the oxidation done, how do we measure the oxide thickness? We use ellipsometry. So this is, you'll get a handout tomorrow on the clean room paper, so that you can keep inside the clean room. And that's something which will follow that handout. The next chapter is diffusion from next week, and the updated office hours of the GT. Homework from oxidation due on 7 days from now, right? So you can look at the book. What are the questions? So we have been touching upon the basic processes. So etching is one process which we use to remove material. So we want to remove material in a wet environment using wet etchant, or maybe using some gases in plasma. So both require their own recipes, both require their own setting up, and the results are are different. So each one of those have their own pros and cons. So in dry etching, what essentially we do is within a chamber. So this is all within a enclosed chamber. We create plasma while we have applying a field across the chamber. So this plasma results into generation of ions, and those ions accelerate in response to the field that is applied, and they hit the wafer once they get here. So once they hit, they result into some chemical reaction. They remove the material that they are supposed to etch. So our recipe is designed in a way that we etch certain materials, but not something else. So what we call selectivity. So it may be the hard mask we are using, or not maybe hard mask, we may be using photoresist by itself, but selectivity is what will cause this reaction to be different at the surface of the wafer. That will result into different material being etched at different rate. For silicon, we have many different etch chemistries that we use, composed of a number of chemicals. So why would one prefer one recipe over the other? Depending on what are we using as a mask and how fast do we want to etch. So there, and what kind of gases we have available. So not every equipment or every lab is equipped with all of these gases. So you see there's a whole bunch of variety of recipes using helium, there's silanes, chlorine. So that and selectivity between different materials that we might be using. So suppose I have silicon dioxide on single crystalline silicon. So this is single crystalline silicon. This is polysilicon, right? Silicon nitrate oxide. So suppose I have silicon dioxide as a mask material over single crystalline silicon. What recipe would I want to use? What would be the best recipe that you would want to use? What is the data that you should be looking at?
Silicon hexafluoride?
Okay.
So sulfur hexafluoride.
Right. So of course, first thing is what gases we have, right? What recipe can we use with that equipment? So suppose we have all of these available. Now what would define my choice of recipe? H weight between different materials. And that is, what do we call that? Selectivity, right? So one recipe etches silicon at some rate. Same recipe etches silicon dioxide at very different rate, right? But some recipe may be in the same ballpark as the material that we might use as the mask, right? So if I have silicon dioxide, let me ask again. If I have silicon dioxide used as mask and I want to etch single crystalline silicon, which recipe will I use?
Chlorine and helium.
Right? So third one. Why? Because the silicon etches 10 times than silicon dioxide. What does that tell me? If I have 300 angstrom silicon dioxide and I want to etch 5000 angstrom single crystalline silicon, will it work? Let's say it again. So if I suppose I have silicon and I have silicon dioxide, and this guy is 300 angstrom, and I want to etch 5000 angstroms. Will this recipe work for me?
No.
Why?
Because the width of the silicon dioxide is not sufficient enough to etch 500 angstrom of silicon.
Width of silicon dioxide?
I mean the thickness.
Thickness of silicon dioxide. So before I will get down to 3000 angstrom, my silicon dioxide will be gone, right? So it's 1 to 10. So the ratio is 1 to 10. Do we all understand the point? Yes. So what can I do to still etch 5000 angstrom of silicon while I have silicon 300 angstrom of silicon dioxide? Use a different recipe, okay? Or I can leave my photoresist there once I do my silicon dioxide etch with BHF, right? Because if I go further down, what is the etch rate of photoresist? Yeah, it's higher than silicon dioxide, but but it's about half of silicon, right? What does it take for me to put a photoresist film? What do I have to do to put the photoresist film?
Just put it on the
Spin it there, right? So all it takes is just put it on there, spin the photoresist, and of course there's baking steps and all that. And I have to do my lithography to open this in silicon dioxide. But what I can do is I can leave my photoresist on after.
Are there issues you run into with when you mix them, such as the etchant getting in between the photoresist and the silicon dioxide?
Anyway, I'm going to get rid of my silicon dioxide. I'm using silicon dioxide just for.
I say, are there issues in calculating how fast you're going to etch?
Yeah. So let me, because you missed the first slide. So the question is, would it etch and get inside photoresist and silicon dioxide? Would it? Those who are here from the second slide onward, would it? Remember, what was the?
Depends on the anisotropy of the etchant.
No, it's what was the dry etching process? What do we do? What is the first step in that chamber? You apply a bias, right? The bias gives directionality to the ions. So if she since so this is right here. So this field is giving the directionality to these ions from the past. So yes, it's a valid concern that this can happen, but no. Since we have applied the bias, most of the etchants will move vertically, right? Most of them will move vertically. So now let's get back again. I say this is what you guys. Which one did you get? You suggested which one? This one or this one?
Below one.
This one.
No, the one that.
Third.
This one.
Just below that.
This guy.
Yes.
Right? So it was, if I have silicon dioxide, I had 385,000. Let's take it 400. So, okay, this variation can be effect of many things. Can be how good is the plasma, how good is the power transfer in the chamber, right? How quickly can we suck out the byproducts? But even if I take the upper value, I take it like, suppose it's 4,000 and that's 5,000 and it's 400, so anything less than 400 will be gone. So to get there, this has to be, so I can easily calculate what is the minimum photoresist thickness I need. And you'll be glad to know that we always have much more higher thickness of photoresist once we do lithography, if the feature size are not very small. Right? If the feature size is 1 micron, you can have a micron thick photoresist. A micron thick means how many? 100 nanometers, right? 1,000 nanometers. 1 micron.
Yeah.
1,000 nanometers, 10,000 angstrom. So that will be more than enough to do this 5,000 angstrom etch. So we have to see what do we use as the mask material, and we have to know that at the end of the etch, how much of that mask material will be left behind. Would it be enough to protect this part which is not supposed to be etched? Right? So these recipes are carefully chosen to do the etch that we need to do. Right? So this is something which is just probably now 7 years old data. There's new chemicals come up, new recipes come up, right? So there's new processes that come up. So it's always a good idea to see the current literature and what are the selectivities between.
Are there tables, of all these things published, or do you have to find the paper that?
Yeah, there's much. If you pick up any review paper on any of those, you'll have plenty of.
Or I should ask, are there handbooks? Is there like one handbook you can go,
So
like you do in chemistry?
So this handbook is, I know they have come up with a number of editions by now. So yeah, there are certain handbooks which have become like a to-go place where we. There is, I tell you, first thing that I look for, there are some certain websites, MEMS Exchange, things like where people share their expertise. So if you are working on some recipe, if you are looking at some process, there are places where you can ask people who are.
So they're not jealously guarded. Like
No, these are very simple process. Yeah, there is nothing too intellectually special to safeguard in those things. Right? So then the concept of isotropic. So generally an isotropic etch is something that has equal effect in all directions. And an isotropic is an etch that has selectivity not just within the material, but selectivity in terms of direction as well. So it's what we can call it affinity, chemical affinity in certain direction, or the etch rate is different in certain directions, so it can be defined in many ways. But the idea is that if you look at dry etch, so this would be something what will go in all directions, but in an isotropic etch will give us what we call high aspect ratio features. So, and why does it happen? Because a field gives the direction to ions, so they travel straight. But then, if in simple dry etch process, it's called RIE, reactive ion etching, RIE, they cannot go too deep, because once they get into something which is high aspect, they tend to collide with the walls. So and the reactants cannot be, the product cannot be removed too fast before new etchant comes in and etches further. So there's limitation on how deep we can etch using what you call RIE, reactive ion etching. So there is limitation on how deep can we go. Just that, and limitation on how deep can we go while maintaining reasonable vertical walls. Because what happens is, if there is no anisotropy, we end up getting something like that, right? Or we have the defects, we get something like this at the bottom. So all of these things are not what we, most of the cases is not what we want. We want something which is, this is still wide enough to show these arrows. It's supposed to be very, very small horizontally, very deep vertically. That's what is called aspect ratio. So there is limitation with RIE, how deep can it go? When it says there is limitation, of course, we have found some solutions. So there are some techniques what we do to make very, very deep trenches or high aspect ratio features. Is it important for silicon devices, transistors, especially what we are focusing? Yes. When we're talking about isolating two devices, we make those trenches and fill up them with silicon dioxide. They are much more used or looked at for MEMS fabrication, which is more three-dimensional structures. Maybe not for electrical devices, but those MEMS structures, these are used a lot. For wet edge, the anisotropic definition is slightly different, because in this case we don't have directionality as such going straight away to vertical, but we have directionality against the different crystalline planes of the single crystalline structure, which means that wet edge can have anisotropy only for single crystalline material, not for polycrystalline material or amorphous material. Does it make sense? What would be the mechanism for anisotropy for wet edge? This big one.
Crystal structure.
Of course, that's what I said. Depends on crystal structure, but why? So different crystal planes will have different number of
atoms that they present.
right?
at
So
that point.
that are present for reaction. Right? So even if we start on a plane surface, after a while, the etchant starts etching one particular direction much faster than some other. So this is a close approximation of if there's single crystalline silicon with 100 in this direction, then this is 111, and this is just a slice. Essentially, this would be an inverted pyramid, right? You know pyramid? There are 4 triangles, right? And there is the center. If you invert it, you have 4 sides of that trench, and each side is a rectangle. Not rectangle.
Trapezoid.
Not rectangle.
Triangle.
Triangle. Triangle. So each wall is a triangle. Mixing rectangle. So each wall is a triangle, right? And they may not get to the edge, right? If you do it long enough, ultimately it will end up into this pyramid where the equivalent planes of 111 will be exposed. There will be no 100 left in there. right? So that's something what we do with silicon. We'll look at that. Silicon, and what we use is KOH or TMH. KOH is potassium hydroxide, TMH is tetramethyl ammonium hydroxide. We'll look at these guys when we go to the H part. So what do we want from H? We want it to be selective, that it can have different affinity for reacting with different materials. So they can have different H rate that will give us this material that can be used as a mask. So etching happens only away from whatever is below that mask and not to that material. This is an example of a screwed up etching where the mask material has been etched from the side, and this was supposed to be a corner, but this has become a circular shape. But we see that the lower material has been etched, gives you a very non-uniform field. So that tells us that this is not uniform. So if it does something like that, it would be very, very variable on different dies. So there is no uniformity. So we want to have uniformity of etch from one chip to other chip, from one wafer to the other wafer. So on one wafer, we have different dies. It should be the same all over, and from one wafer to the other. It's not an easy job. So once we get there, we'll see why. And we want to come up with processes which are cheap, which do it fast. Do you need some napkins?
No, I'm good. I'm good. Sorry, I'm not trying to disrupt the class.
Okay.
If you need bars from bringing beverages.
No, but if you are in trouble, we should help you. Get some napkins or something. So, and then some places we need it to be mesotropic, some places we don't. What we get at the end is, again, surface quality. We don't want it to be rough. We may want it to be rough. It depends on what we are doing. What is left behind after an etch is, again, important. If we have KOH for etching, to leave behind potassium ions, which are bad. They are fast diffuser. If you heat the wafer up, they get into the crystalline structure and disturb the electrical properties. So there are all these things that go into defining an etch process. So with etch we remove things, with deposition we deposit materials. We can deposit a very large range of materials. We can deposit amorphous materials, we can deposit single crystalline materials, while using special processes where we have something which is already crystalline, we can deposit material on top of that in crystalline form. Can be done just by physical deposition, where we are more concerned about adhesion between different materials, or it can be a chemical deposition where we do some reaction, maybe in the chamber, and then product is deposited on the surface, or we want some reactants to get on the substrate and do the reaction and result into a film formation. We do deposition of many things. So in physical vapor deposition, simple idea is we have this high purity source material here, and we evaporate it, we melt it. When something melts, it evaporates. So when it evaporates, it goes into the open direction, which is the top. Once those atoms are traveling, the first surface they come in contact with, they adhere to that surface, and we put our wafers on there. We do it under high vacuum. Why do we want to do this process under high vacuum?
To avoid impurities.
To avoid impurities. All right. What else?
For better adhesion.
Better adhesion. I don't know why, but maybe. What else?
Wet collision.
To
Wet collision, so material.
Avoid collisions. Okay, if we avoid collision, what happens to the travel of atoms?
Straight line.
Straight line. What do we call that lack of collision? Increasing mean free path. Right. So we want to. What is mean free path? Again, if I open this bottle of fraternity in this corner, so those atoms of perfume travel, but while they travel, they are colliding with each other. So there's collision between atoms, so there's mean time that we calculate that. They have some free travel and then they collide with something, change direction. So those collisions are elastic. Right? By providing a vacuum, we are taking away most of those atoms which may be in the chamber. So essentially when an atom evaporates from the crucible, that pot where we have molten it, it essentially travels in straight line up to the wafer. Right? So
Does that include the surface, increase the surface quality?
so we don't lose any material to the walls of the chamber. And what we get is essentially straight from that pure source comes to the wafer uninterrupted.
I see. So is it smoother that way?
Okay, now the growth of film is a factor of many other things. Right now we're talking about when you pump down the chamber, essentially you're increasing mean free path. So they would get to the wafer unimpeded. Right? If you allow the collisions to occur, they will go in all directions. So you lose much of the material. This 95% plus pure metals are not cheap. They're very expensive. So you want to do this. So this pumping down is done to, it's called cryo pumps. They are very, very efficient pumps. So we have to, in many cases, have to put liquid nitrogen on the pumps to keep them cool. They are such, it takes you down to, I don't know, 10 raised to minus 8 sort of torques. So it's done mostly for metal deposition, but now it has been replaced with what we call CVD, chemical vapor deposition. So chemical vapor deposition is essentially same process as reactive ion etching, right? In that case, the etching where we had that plasma generated and we were making ions to travel to the wafer and they react with this chemical and etch the material away. If we change the recipe and we have something which when it gets to the wafer, instead of etching it, it gets adhered to that surface. So that's called deposition. So now we are adding material. So it's same idea of plasma wafers. We have field applied and we give an RF power to maintain the plasma. We get material deposited on the surface. There are a couple of different types of CVDs. One is called plasma enhanced CVD, which is this case. There is another which is called LPCVD, low pressure CVD. Low pressure CVD, we don't use plasma, but essentially it's again a chemical deposition process. So since we'll look at these later on. So in LPCVD, we supply a number of gases, maintain low pressure. The reaction results into some products which get deposited onto our wafers. What happens during the deposition process? We have reactions that may occur in gas phase, which may occur once it gets to the surface. And in either case, they start accumulating and result into formation of a film. Right? So we have this chemical reaction that results into film formation. So there's for that reaction, we have to supply energy, which is either coming from plasma or from heat. So this is PECVD is very similar to RIE. LPCVD is very similar to oxidation, right? But the difference is in oxidation we are not doing any chemical reaction except oxidation itself. In LPCVD, our reaction depends on the gases that we supply, right? And that results into whatever material. So for LPCVD, we keep the furnaces dedicated for one type of material. So if we do polysilicon deposition in a tube, we use it for polysilicon, always. If I do it for nitride, we do it for nitride almost always. So many different types of materials can be deposited using different recipes. So like we had recipes for etch, we have recipes for CVD. Right? In this case now recipe is again similar way before, combination of gases and reaction rate. Okay, reaction rate is what we want to control from some external parameters, which is gas combination, pressure, temperature, power. Power is a very important parameter because your reaction is consuming. When your reaction occurs, you're essentially taking away the ions from that plasma. To maintain that plasma and to ionize further gas that is coming in, we need to continuously pump in RF energy, right? We have so many electrical engineers. What do we need to do when we do RF energy transfer from one medium to another medium?
Match the impedance.
Match the impedance, right? So RF power always, the first thing is we have to do match the impedance, right? We do that for our stereos, speakers, right? They have impedance and then what happens if impedance does not match? Maximum power is not transferred. Refraction or reflection?
Reflection.
Reflection. And what happens when power reflects back? Damages?
Yes, if some anti-refraction, there's some damage on
When it gets back to your power supply, it's gonna fry your power supply, damage your power supply. And while before it happens, you're gonna have standing waves generated, which will be radiated if the wire is too long. It's gonna act as antenna, right? So during the process, we have to keep an eye on plasma. How do we make sure the plasma is on and maintained? Have you guys seen plasma? Right? Have you guys seen Back to the Future? It's a very old movie. How do we see plasma? What do we see with plasma?
Lightning.
Glow. We see glow, right? So that glow tells us that so there are eyepieces where you can see there is indigo type of glow in there. So for RE, for CVD, PCVD, plasma is maintained, and we have to keep an eye on power supply as well as the chamber itself.
So you're actually keeping the plasma energized with RF?
Because whatever you are creating is getting consumed, going down on the surface.
I see. How do you get the plasma started? Is there like do you have to ignite
By
the plasma?
switching off a button. Yeah, so you
For our
start
purposes,
with
I
low energy, so you have to pump the power gradually to the level of whatever your recipe wants. Yeah, so it starts with very low power, and then you gradually get to your actual power that your recipe requires. Right? So these two, PVD and CVD, do deposition of amorphous materials, amorphous without any crystalline structure. But we know now that we do make many layers of devices on our wafer. How do we get crystalline silicon on top of something which has been covered in sputtering? Right? Sputtering is another way of depositing here. But epitaxy is a process where we deposit crystalline films, so we can use them for next level of devices. But essentially what we need for epitaxy is one layer of or what you call the terraced layer of crystalline material, and then we can grow crystalline material film out of that. So we have the underlying crystal and we grow it on top of that. Now, the devices that we make, they are made in epi silicon. Okay. For epitaxy, mostly when we say epi, that means epitaxial silicon. So once you get wafers in industry, those are already, we already have epi grown on top of them. And we use that to create our devices.
What's that layer called again? The
Epi.
first layer?
Epi, EPI, epi. It says epi silicon. Right? And we do that again in CVD. Right? But now, the differences are recipe and the underlying crystalline structure. And there is a specialized equipment called MBE, molecular beam epitaxy. We had one MBE here in Narofab. I think that's decommissioned. It's a very complex equipment, but gives you very exactly the same film grown on top of what you already have below. Right? So it's a very simplistic picture of MBE system where you have electron gun to evaporate material, and you have substrate held up there, and you get the material deposited at that level. So again, it's pumped down to have low pressure, so you can reduce the contamination and have higher mean free paths for the travel. We'll look at EPI also once we look at those processes in detail. CMP stands for chemical mechanical polishing. So after one layer of devices, we need to flatten out the playing field and start over again. Once we get to the next level of device, we have to flatten out. So it's a combination of mechanical and chemical sort of rubbing of a wafer, but it's very fine rubbing where your surface roughness is within a few nanometers. So it's a very fine polishing process. So it depends on if we are concerned in planarizing just in a small region, or if you want to do planarization over the whole region. And essentially, let's say the process, if you break it down simply, there's this holder which is keeping the wafer face down and it's rotating, and then we have this polishing pad which is, again, that is also rotating. We are looking at the pad, whatever comes out of that polishing process, we want to clean that, and we want to apply further liquid called slurry, which keeps the polishing going on. So slurry has things that chemically wet or has grains, which basically rub the surface to remove the material that you want. So it's a very well-controlled process, but very dirty process, because slurry is a dirty liquid, and then what comes off of wafer is also contamination. So, but CMP is what we do after every level of devices. There are some planarization processes which we call non-CMP planarization. A simple one is we spin on glass. So just like photoresist, we have liquid glass. Spin it on a wafer and heat it. What we are left with, a plain glass layer. That's called non-CMP planarization.
Now, do you do that after
Yeah,
you
once
deposit things or before?
Yeah, once you are done with your surface and you have made your contacts, and now you're ready to make a vias, spin it, open your vias, and you have next level of device fabrication on top of it.
see. Why would you want to spin glass onto your electronic device, though? I mean, wouldn't that kind of cover up your contacts and everything? Or
Yeah, we make the contact. Okay, so you on one layer we have run all our lines horizontally, right? What we call interconnect. Now to get to next level, we have to make this vertical connections, what we call VRs.
I see.
So I've run my pipelines, and now I put my road on top of that, and wherever I need a connection underground, I make a vertical opening, which is what we call VR. I'm giving an example of switches, right? So before I open my connection, we cover everything, right? We make a road, or we pave everything, and then we open those for individual home connections.
So you can make multiple layer devices.
Right, so then
I
you
see.
have multiple layer of devices. So spin-on glass is one material. There are many other materials which are used now to planarize, non-CMP planarization for devices. Right? Reflow, deposition, spin-on glass. So yeah, there are other planarizations. Right? So this probably is. So far we have touched upon all the basic processes that we will do and we'll look at. Probably we won't do all of them. We don't have CMP here, but anyway, you'll do one layer of devices. We'll look at a very, very fundamental process, oxidation. I could have put photolithography before oxidation, but oxide is something that we can grow on a bare wafer, right? For lithography, first we have to have some material what we can want to use as a hard mask later on, right? So oxidation comes probably before lithography. So let's start with oxidation. It's again, if we grow out of silicon, we call it growth. If we deposit, we don't call it oxidation. We don't even call it oxidation. We call it oxide deposition, because that's a deposition process. So whenever you hear or read oxidation in your diagnostic exam or exam in this class, oxidation will mean thermal growth of oxide, right? And then there will be two types, either wet or dry. And we'll see what are the difference between wet and dry. Some very basic features should tell you what kind of oxide is being talked about, right? Some basic features of oxide should tell you very easily what type of oxide is being discussed. And we'll see what are those properties. You guys, I hope, have read the paper, field growth model on oxidation. I have some simple equations from there. We'll see. But that model is not used for thin oxide, because thin oxide is a very fast process. But once you get into above that thickness, then you have a barrier to the oxygen species to get to the interface. Then the Elo model is more applicable. Before that, it's a very fast process. What happens at the interface? What happens to the dopants if you do high temperature process? So this is interface of silicon and silicon dioxide. So you can tell your friends that we can see atoms. This is essentially atoms, right? So you see that periodic structure there, which breaks down in silicon dioxide. There is still limited order in silicon dioxide. That limited order is what makes one type of silicon dioxide better than the other, right? Where do we see different types of silicon dioxide?
Quartz versus regular
Quartz,
glass.
glass, right? Silicon dioxide that we grow. So they are very different in their brittleness, their physical properties, right? As well as chemical properties. So which we'll look at what are the differences. What are systems we use? And where do we use those silicon dioxide? As a very simple discrimination of whether we use wet oxide or dry oxide. Just remember that dry oxide is slower to grow. It is very fine in quality. So fine oxide is used. It grows slow, so throughput is less, but we use it only for gate oxide, because at gate we need fine quality oxide. Dry oxide used on gate, it's slow to grow. Most of the other oxide will be wet oxides. If it's field oxide, it's too much area need to grow. We want it fast because the quality doesn't matter. Electrical quality doesn't matter there. So these are all low-cost STI liners. Polyreox are what we call as field oxide. Can be, they are wet oxide.
What's the low cost?
Local oxidation of something. We'll look at that. It's a localized oxidation of silicon. So, if I have gate oxide, I need it very thin, I need it high quality. So we do, what kind of oxide do we do? If it's thin gate, what kind of oxide would we do?
Right.
Dry oxide, right? But if the thickness goes high, other types of field oxide, masking oxide, what kind of oxide will grow? What kind of oxide will we grow? Wet oxide, right? And native oxide is something which is very, very thin. And in dry oxidation, we have just oxygen, and wet oxidation, we have water vapor that is used during the silicon dioxide growth. So that extra hydrogen results into low porosity silicon dioxide. So it has high porosity. So it has more porosity, which changes its etching property, which changes its electrical properties.
So this is dry oxide, right?
Which one?
You were talking about the extra hydrogen.
So
The wet oxide. I'm sorry.
there's
Yeah.
two lines. Right, so etch, the wet oxide and dry oxide, they have different reaction that occurs. So without vapor, if we have just oxygen, that creates a better quality oxide, but it's slow to grow. And essentially its electrical property and ease in growing is what has made it this insulating material. But since we are becoming very close to a few atom thickness of silicon dioxide, it's becoming less dependable, because physically it's become so thin that electrical tunneling is occurring through this. So we need some other material which has same dielectric contribution but is physically thick. So we use high K dielectrics, in which the end result with high K and higher thickness, the end electrical coupling is the same. Right? So in certain thickness of silicon dioxide, there is 44% of silicon consumed in it. Right? So what happens on silicon dioxide? We have 4 oxygen atoms that bind to it, creating a tetrahedron structure. Right? And these are paired. These are shared between adjacent tetrahedrons. So, interesting word, amorphous silica, which doesn't have any crystalline structure, but it has bridging of those atoms occurring, which makes it dense or less dense, which makes one oxide different electrically than the other oxide. So, how many types of oxygens are there? Bridging and non-bridging. So, if I have many more of bridging oxygen species, my oxide is better or worse?
Oxide is more crystalline then.
It's much more crystalline. It's much more dense. It's less porous, right? So, is it going to be electrically better or worse?
Better.
What is the job of silicon dioxide? Insulate, right? So we want something which is dense. So that makes one type of glass expensive than the other. That makes bulletproof glass stronger than a regular glass. How dense are tetrahedrons? How many oxygen are bridging with respect to non-bridging and oxygen? So it's a very important criteria because we see glass everywhere. We see silica, we hear silicon dioxide, we see quartz, we see all sort of different materials which are essentially silicon dioxide, which are essentially glass, but they have very different properties. Based on
Optically, the oxide we grow, is it essentially glass? Like, we could actually oxidize a whole wafer, would it become a wafer of glass?
it will be all glass, but it's going to take a few days before you get there.
And we could do that.
Yeah, at the expense of burning
Not that we would want to.
yeah, not that you want, but essentially we'll end up with something which will be a thick glass, telescope glass. And what we can do is we can buy glass wafers directly. Yeah. So think if we glassify the whole wafer, would it be colored?
Probably,
Probably,
if it was doped.
but it is doped. I don't know. Do you think the doping is what gives the color to silicon dioxide on top of silicon? We'll look at how once we do the metrology of oxide. We'll see
No,
what
not
gives-
that color, but you can dope glass to
It's a
color.
reflection. It's the internal reflection. If there is no reflection, it will be all transparent. Right? So, bridging and non-bridging. And that gives long range or little long range structure. So, what we grow thermally is dense, robust, and very good insulator, and gives a clean interface with the bulk silicon. And we can have impurities embedded into silicon dioxide. So we do these guys, which we call network modifier, or we can have free hanging hydroxyl groups. So, and these are bridging and non-bridging atoms of oxygen which are available there. So, what do the network modifiers do? They weaken or strengthen the network. They weaken or strengthen the silicon dioxide. So, yeah, doping is done to make them, give them additional properties. So, what happens in wet oxide is we have many more of hydroxyl groups which weaken the structure, right? So that's the fundamental reason why wet oxide is fast, but electrically not good. Electrically it can result into tunneling and a very thicker film than a dry oxide, where we can thin it and still not see any tunneling of current. Okay. Right? So these are important considerations once we are looking at the physics of oxidation. What are the properties that we look at once we are that makes it interesting for us? It doesn't melt at very high temperature. It can sustain very high temperature. So essentially, I oxidized a vapor, I can use it essentially for everything. Any high temperature process can be done with oxide on, right? Which is good. It doesn't reduce my thermal budget. It doesn't add up to restriction on my back end of line processes, right? So even after I've made a few layers, I can still oxidize. And still, or maybe put it high temperature process, and still my oxidation oxide will be fine. Density would be used for thermal silicon dioxide, which would be less for other oxides. Right? Because in this case, we are making it out of a single crystalline material, which makes the atoms, many more of hydrogen to be bridging than non-bridging. Dielectric constant, yeah, 3.9, we don't do it. So resistivity, energy gap, conductivity, expansion, these are all physical or mechanical or electrical properties which are very conducive for silicon. If thermal expansion was different, way different than silicon, we would have stress issues, right? What would happen if you have stress between two films?
Then you separate,
They separate,
or you crack
so
the
they
whole
can
material.
come up. It can crack the material, right? So even if before mechanical cracking, what it can do is what we call dislocations. It can cause dislocations of crystalline structure. Dislocation is where you might lose one ball of a lattice. So you don't have atoms there. That results into electrical degradation of behavior of device. So and we'll see that in case of epi, once we do epitaxy of different materials, say germanium and silicon, they have different lattice constant. We know lattice constant. Did we discuss lattice constant?
No.
When we were talking about Miller indices. Did we or did we not?
I don't think so.
So that's the, of course, that's the lattice constant is the length of unit cell, one length, right? Unit cell is mostly cubic, so it's the dimension of the cell. So if unit cell of one material is say 1 angstrom, the other one is 1.5 angstrom, and then you draw that on top of the other, the lattice will not match, right? But they will want to maintain that structure. So one will be under compressive stress, the other one will be under expansive, tensile and compressive. So that we don't see that with silicon dioxide, which is good, which is to our advantage. Conductivity is also the same ballpark, which is good. So you can remove the heat, so there is no what you call hot spots at the interface. Energy gap, what is the band gap for silicon?
1.1
1.1?
eV electron.
1.1?
Band gap.
Yeah, band gap 1.1. Yeah. That's the 0.7 is the breakdown voltage.
That's the
Breakdown
0.7. That's the
threshold
Threshold
voltage. That's
voltage.
threshold voltage. Yeah. Refractive index, very different than silicon. And this is what we use to measure the oxide thickness. We calculate that in our formula from the light that is reflected off of silicon. And rest is all H rate in VHF for 50% VHF. So I told you VHF or BOE can be 6 to 10, right? 1 to 1, 1 to 10. Many different combination we get in VHF, right? What is VHF? Diluted hydrofluoric acid. Diluted with H2O2, with TM water, with water, right? So H weight is 1000 angstroms per minute. We always assume that, we always take it as 1000 angstroms per minute. And so once you get into the lab, once you spend some time, it will be very easy for you to look at the color, look at the chart, and you will have a very, very good understanding how thick is it and how long should I etch it. How thick is the silicon dioxide and how long do you want to etch it to remove it completely. Of course, we don't normally remove the whole thing. We remove, after lithography, remove it from wherever we have made our openings. So if your chart says it's 2000 angstrom, you do 2 minutes 30 seconds, slightly above. Generally it's 10% above the time. So if it's 2 minutes 120 seconds, so you do 12 seconds extra, right? I would do 2 minutes 30 seconds to completely etch silicon dioxide. So this is interesting. So high K, we'll look at what is a little more mathematically what is high K. How does oxidation occur? Said before, you have native oxide, right? So oxide starts interacting, converts into silicon dioxide, film starts growing. As film grows, oxygen has to now pass through that barrier, get to that interface before a reaction occurs. So now we have three major parts of that process. One is called F1, where you have plenty of oxygen available, right? So the reaction is almost instantaneous on surface, right? But now it has to travel through that thickness, and flux falls as it travels. What is flux again? There are few definitions I would want you to remember always. How do we define flux? Number of particles, atoms, electrons, holes, whatever, passing through unit area in unit height, right?
It's flux
So,
density.
pardon?
It's flux density.
Flux density and flux, we use it same way. Yes, he's right. It's density, it's flux density, but we interchange it. We call it flux. So we define the three combinations, three different parts of that, the whole oxidation movement. One is at the interface, the other is that it has to pass through that certain. Now while it's passing through, what factor will be important? Once it's going through material, what is important parameter for any solute? So think about it. What is causing that movement? Diffusion. So what is that constant we define when things are moving through some other material?
Diffusivity constant.
Diffusion coefficient, right? How fast it can pass through. Now once it gets to that interface, it's going to react. So what do we define for reaction? To define the speed of reaction or volatility of reaction, we define reactivity or reaction coefficient. This is a reaction, how fast that reaction occurs. So these three fluxes depend on entirely different giants. In one case it's the reaction, which is at the front. The other case is the diffusion coefficient. The third one is reaction coefficient. Now, if I do it where I pump all the oxygen I have, the only factor that will be limiting will be diffusion coefficient, right? Because I have unlimited supply of oxygen coming. The only thing that reduces the rate of reaction here will be how fast they can pass through this, right? If I reduce my supply of oxygen, this is going to stay constant, but now mass of what is incoming will define how much reaction occurs here. So in both cases, the limiting factor will be different. Just like in diffusion we had, okay, when I say diffusion, now I'm talking about diffusion, which is the process in silicon fabrication. What was the difference between unlimited supply of diffusant and limited supply?
The concentration gradient.
In unlimited, the distribution kept on increasing and the maxima didn't change. In limited supply, the maxima came down, so the same number of ions or dopants were. So in this case, again, so in, just like there were different limitation in this case also, the limitation depends either on diffusion coefficient or how fast can we do the reaction based on how many species make it to the other side. Okay, so F1, F2, F3 are written there. So in F1 is how fast can we transfer the mass inside the tube. So oxidation happens in the furnace. How fast can I pump the oxidizing species to get in there? F1 is driven by the concentration difference of oxidizing species, right? And that brings up the question of dissolving something into a solid material. Just like diffusion, we have now oxygen in gas state, and we have hard substrate where we want it to diffuse it. Right? Can't be done at room temperature, it has to be done at high temperature, so those oxidizing species get enough energy to change medium. Right? Change medium. And this is defined by what we call Henry's law, which defines ideal gas behavior. PV equals KT. Temperature is something we have never seen like this in terms of gases before. Right? We have always considered K2 to be constant, where we said, okay, if P goes down, B goes up. Right? And if P goes up, P goes down. Not anymore, because now we have dependence, real dependence on P, where a change in P will define how much of oxygen can diffuse into silicon.
In this case, is K a constant relating
K,
to NR?
Boltzmann is always a constant.
So the number of moles times the Boltzmann constant. I've always thought of there is one that is PV equals nRT.
At room temperature, that's what we do.
So K is a constant we can assume at the given temperature.
K is always constant. K is Boltzmann. Right? The point here is that we seldom do this because we don't raise our temperatures and we don't make our gases travel from gas to solid. We seldom see that ever. Do we?
Generally not.
But in silicon, that's what makes these things happen. In diffusion, which is the introduction of dopants, and it's also diffusion here, because we have to get the oxide species to get to silicon to react. So, partial pressure of the species in the gas phase. So, by changing the gas species in the furnace, I can control my oxidation. Right? I can use nitrogen to reduce the fraction of oxygen in the furnace. Why do we want to do that? Why would I want to dilute my concentration of oxygen in the furnace? To control the process, to get to very thin oxide. And thin oxide, why do you want thinner oxide? Very thin oxide, because to device scaling. Right? So we have one. So thin oxide or thin films is a very specialized field itself. And thin oxide itself is very hard to achieve, because it's not just we want it to be thin, we want it thin over the whole wafer. We want the uniform thickness over the whole wafer. Right? And once we are doing just 1 or 2 or 3 atom layer, it's very hard to do that. So we want to control by controlling the reaction rate. Now, in that case, diffusion through that existing oxide layer will not be rate limiting process. It will be how much mass we are transferring. So F1 will become limiting factor in that case. And why we would want to do that, we don't know, right? To control the growth rate of oxide. Does that make sense? No? Does it? Some?
Do thin oxides have the same quality that otherwise?
Yeah. Unless the voltage results into it, the high voltage results into breakdown, then tunneling starts occurring. So tunneling is the major challenge with thin oxides. Otherwise, they are exactly the same. They're just thin.
Except for their thickness, voltage can break it down easily.
Right. So then it becomes easy for the voltage to break it down.
So, I have a question that may be a little bit off scope. When you damage a device, say with static electricity, what's really happening? Are you breaking down that oxide insulation?
Physically?
Yes.
No, tunneling is not physical.
Not physical. Let's say I have a microchip. I touch it. A spark comes off my finger. I fry the device. What's really happening?
Frying is.
Well,
That's
I know it's not technical.
that's a static. You're basically overloading. You're applying too much. Yes, if you apply too much voltage, it physically burns, so to speak. Right?
I see. So I'm destroying these insulation layers.
You are destroying the material in, I don't know what phase. It may not be the material in the device itself. You might just burn the interconnect.
I see.
That may be metal which burns away. Just
That
like
makes a lot more sense. That makes a lot more sense. I might be burned it.
So I don't know if you guys remember those old-time fuses where we had this big socket that had to be wired up. So we had this wire, and you guys remember that? When I was too young. Remember those? So those were wires, and we would plug it in, and when the fuse would blow up, you would take it out, and you'd see that wire was burned from the middle. It was called electromigration. Electromigration is a real phenomenon in devices. There's miles, remember that there's miles of interconnects that we have laid down. I'm not talking about the area or how thin they are, but they are miles long. Anyway, if you cause them to break, electromigration, you're going to fry your device. You're going to fry your IC. But devices will be still good. So that's why many times if you might have two of the pins not working in an IC, rest may be still working. Have you encountered that?
Not yet.
Yeah, that happens in third world. So where I spent 10 years repairing those ICs in a ship, we would look, okay, what legs are still operational? So if that is still operational, okay, we don't throw it away. We might be able to use it somewhere. So that's a sidetrack question. But let's get back. So F2 is what we get from Fick's law, which is diffusion through that layer of silicon dioxide. Again, it depends on the concentration gradient and diffusion coefficient. The third one is the reaction rate, where it will depend on C1, how much, or Ci, how much concentration of oxygen we get there, times the reaction rate. So Ks is what is reaction rate constant, which will define how fast our reaction will go. So F3 will depend on how much of oxygen makes it through to that interface, which will result into reaction going fast or slow. Questions? Yeah, they have assigned the homework, which is in the second or third slide. Lab starts tomorrow. No material goes in the clean room, nothing except just you, right? And a pen maybe. You have clean room notebook which stays inside. Clean notebook that stays inside.
Can we use the lockers if we bring out a locker, or is that?
These lockers, yeah, those lockers are meant for you guys. So put everything in there. After you cross that mat, you have no belongings with you. You have nothing. Like your bags, your water, your coffee, your spinach outside of the room.
No newspaper to sop it up with.
It's all inside. Right? I'll be around tomorrow. I'll be out of town for about a week. GPA will teach next lecture done. But I'll be reachable via email.
Do you know what we're doing tomorrow? I don't think we received the
That was
lab.
also in part of second slide. Oxidation. Cleaning and oxidation. And ultimately ellipsometry. So he'll give you the handout tomorrow. We'll follow that. Right?